attention that in one of my hours last Friday we didn't talk about covalent. Polar, nonpolar, or metallic or hydrogen bonding, because we just talked about this virus. That was second hour. Even if you were there Friday, this will be a good review as well. So we spent a long time, in fact 2 days, doing ionic bonding and talking about it and doing a lab. This is covalent, so I just want to talk about real quick what the difference. So just make a quick flow chart. If we have bonds, we have basically two main types of bonds. One is ionic, and then one is covalent. Now the difference between these two, in covalent, they have to share electrons. In ionic, they steal and lose electrons. And that's between a metal and a non-metal. All right, so that's kind of the basic 2 to 2 or 1 to 1, like one ionic, one covalent, but there are two types of covalent bonds. And it still has to do with how they share. If they share unequal, we call them a polar covalent bond. If they share equal, we call it nonpolar. All right, so let's see. Unequal. This table's shaking, so my video, I'm sure, is shaking. And that says unequal sharing. Let me move back and I won't touch the table. Then nonpolar, we have equal sharing. Now we're all talking about the electron. In all of these bonds, the type of bond that they are depends on what happens to this electron. Okay, so this is a polar bond is when you share unequal, and polar means two-sided. So when they don't share equally, what you end up with, you have two atoms, and the electron will draw a probability cloud. It resides mostly around 1, and that makes this side slightly more negative than this side. So we call it polar because it has a two-sided molecule, a positive side and a negative side. When you have a nonpolar, you basically have two atoms and the electrons are shared equally around them, so there's not a positive or negative side. So we would say it's not two-sided. Okay, that's all that in a nutshell. Now let's just go ahead and fill in the notes. So covalent bonds, atom with the same or nearly the same electronegativities. Oh boy. Yep, I had to scribble. Tend to react by sharing electrons. The shared pair or pairs of electrons constitute a covalent bond. Okay, so they will share versus ionic, which loses and gains. They usually occur between nonmetal atoms. This is a good important thing there. Since a metal and a nonmetal, their differences are so great in electronegativity, they don't share. They have to lose. So a bond between two nonmetals has to share because their electronegativity differences are small. And this is the value that's the cutoff, and that's on your periodic table on the far right side as well. There can be a sharing of 1, 2, or 3 pairs of electrons in a covalent bond. So this shows you an example of each. In this, fluorine needs 1 pair to share, so they just come together and share this pair right here. And we draw that as a line. Oxygen needs to share 2 pair or 2 lines. Nitrogen 3 pairs or 3 lines. So covalent, just the word covalent means together. Co, together, valent, valence electrons. This is a matching term on your exam. Covalent is the general term for sharing electrons. I know my handwriting's terrible, but hopefully this year you've been prepared well for that. Okay, so just covalent means we share, but there are two different types, Polar covalent, remember that means it's two-sided. So in this example of water, we have the electrons move towards the oxygen, making it slightly negative and leaving this slightly positive. If we divide that molecule in half right here, we now have a two-sided atom. One side's negative, or I keep saying atom, I mean molecule. One negative side, one positive. Okay, so no two elements have exactly the same electronegativities. Because of this, when covalent bonds form, one of the atoms more strongly attracts the valence electrons of the other. This unequal sharing causes one atom to be more negative and the other more positive, once again making a polar or two-sided molecule. Polar bonds have electronegativities of 0.6 to 1.7, and you're familiar with from biology that water is polar, meaning two-sided, meaning the atom has a the molecule has a positive half and a negative half. So that's polar in a nutshell. And then there is nonpolar. These have really small differences. They're less than 0.6, or 0.6 probably. Since they don't pull harder on one side or the other, they have to share most equally. So because of this difference is so small, the electron attractive force of each atom are almost equal. This results in a molecule with a relatively neutral charge. So this is like if you were to arm wrestle your twin or yourself. You know, it'd be really, really hard to beat yourself, but whatever. So that's nonpolar. That means not two-sided because they're sharing equally. Methane is an example of that. That's natural gas. Here we'd have C, we'd have an H, an H, an H, and an H. Okay, in another video we talk more about the physical properties of this, so that I won't spend too much time on that. So then we get to metallic bonds. The metallic bonds, they behave weirder than anything we've talked about so far. In a metallic bond, we're talking about a pure piece of metal. So just like a chunk of aluminum. It's not bonded with anything, it's just its own atoms all kind of mixing together. So in a pure piece of metal, the valence electrons are free floating among closely packed, positively charged ions. The C of floating electrons are what gives metals their physical properties. All right. So it says contrast the effects of free valence electrons to that of a charged ions in an ionic bond. So what that's saying is in a piece of metal, like this electron is free to go wherever it feels like. Because really none of these nuclei want it, but all of them want it, all at the same time. It seems kind of weird, but if you just throw all the electrons out to move wherever they feel like, then all the metals can feel as though they have a full valence shell, when in reality they have too many. They just send them out to play. An example of this is when you're at a church on Sundays. You're in the chapel, you know, there's all these people sitting in their benches, and then just some little kid goes rogue. So he escapes his mom, and he comes over here and over here and over here. And no one really cares that much. The mom's not that worried. Everyone in the building's not really that worried, because at any given point in time, there's like 40 moms in here that can take care of that kid if there's a problem. So kind of, it's a little weird, but at any given time, nobody owns this kid and everybody owns this kid at the same time. It's just like the electrons in a pure piece of metal. And that's what gives them their properties, like their ability to conduct electricity. If an electron here has no reason to stay there, if I can give it a force or a push, it will move because it's free to go where it wants. And that's when we have current flow, or what we call electricity. Metals are the only things that are good conductors because they're the only things that have free floating valence electrons. Okay, the final type of bond, this is sort of my pet peeve in science, is hydrogen bonds. Because hydrogen bonds are not really bonds. They are attractive forces in which hydrogen that is covalently bonded to a very electronegative atom is also weakly bonded to an unshared electron pair of an electronegative atom in the same molecule of a nearby molecule. So hydrogen bonding happens in water and other things too, but mostly water when we talk about it. So we have O, we have hydrogen. Since we just barely said this was polar, we have kind of a negative side and a positive side to these molecules. And so what will happen is the hydrogen on one water will form a attraction, a weak attraction, but it's still an attraction, to the oxygen on another. So what this does is it causes the actual water molecules to stick to each other a little bit more than they normally would because of this hydrogen bonding. Now, it does exist in more things than just water. If H and you have an N, an O, or an F in another bond, the H can be attracted to those as well. Those are pretty much the only time you see hydrogen bonding. But one more time, it's not technically a type of bond. It's an attractive force where two like molecules will attract to each other. But they're pretty easy. If you saw the magnets on my desk that were water molecules, this attraction right here is like when one magnet attracted to the other. The red would attract to the white, but we could easily pull that apart. This force here, the covalent bond holding them together, was like it was glued together, so it'd be significantly harder to pull apart. Okay, that video went a few minutes longer than I planned, but hopefully that helps wrap up these type of bonds.